Welcome to this web lecture about the graphical aspects of graphical user interfaces. When we are designing graphical user interfaces, we need to take into account the properties of the hardware and software that we use. There are limitations of the bitmap displays that we use. And when we use them carefully, these limitations will not have a negative effect on the user experience. In a separate web lecture, we will also discuss the aspects of the window system, of using windows and several techniques to make a presentation smooth. In yet another web lecture, we will talk about handling events, handling the input that the user gives. So let's first look at the bitmap display hardware. On the left, you see what we have in raster graphics. In raster graphics, the letter that you see here, it's built up with small blocks. It's just like building it with Lego blocks. The edges of the letters are not smooth like they are in the vector graphics display on the right. Vector graphics we still see, for instance, in laser shows. We see images that are projected on a wall or sometimes on the clouds. And they are generated by shooting a laser beam across several fast-moving mirrors into the sky or onto a wall. The beam is moving and can move in any direction we want. In our bitmap displays, we have a large array, a rectangle of points, of dots, and we can only decide which color to use for each of these dots. Our graphical display systems can be used in two ways. There is some hardware that can perform graphical operations. It's called the graphical display system. It's typically on what is called the video card in your computer. So you can ask this system, for instance, to draw a letter, and it will compute which pixels need to be colored to generate the shape of the letter. But we can also ask the main CPU, the compute part of our computer, to decide which pixels should be colored to generate a letter, and it can also access the display memory. So that memory, which can be accessed from two ways, is called the frame buffer. Now that frame buffer is then copied to the screen. So our computer monitor will refresh its whole image, that is a copy from the frame buffer, typically around 100 times per second. We think that we are seeing a steady image, but we are actually seeing an image that is shown only very briefly, but in very rapid succession. And our eyes cannot register that these are separate images that are shown. So we just see it as if it was a picture frame. Let's look in detail at this slide that shows us some lines and letters. As they look, we have emphasized, enlarged the effect of the bitmap display. And when we look at the lines, we see that some lines, like the one on the left and the one on the right, look very nicely. They look like they are drawn with a pencil. Some other lines show an ugly effect that is typically called the staircase effect. And this effect results from the inability to position colored dots anywhere on the screen. We are limited to the coordinates in this raster that exists. If we look closely at the letters on the bottom, and I were to ask you, which of these 4 letters is the best that we can show with our black dots on the white background? You might answer, you can think about it for a moment, and you will probably answer that the letter on the left, which looks the best, must be the best we can do. Actually, the second one from the left is the best we can do. The best letter on the left is produced using a technique that is called anti-aliasing. The second letter shows a little bit of staircasing effect. And what we've done is we've added some gray dots along the edges. And the gray dots, which you can't really see, give the impression that the slanted edges of the letter A are actually smooth. Anti-aliasing is especially important when the resolution, the number of dots available on our screen, is limited. The best screens we have today, like the so-called retina screens on the latest iPads and MacBooks, they have such a high resolution that even without anti-aliasing to help us out, the edges already look smooth. Now regarding color. Every dot on the screen can be shown in a number of different colors. The number of values we have available depend on the number of bits we use to represent the color. If we have 1 bit available, then only 2 colors are possible. Typically, they would be black and white. Since memory was initially very expensive, to have good color reproduction, systems started using 15 or 16-bit color representation. With 15 bits, which is 3 times 5, every dot that is actually made up out of a bit of green, a bit of blue, and a bit of red, could have 32 shades of red, green, and blue, and that actually generates pretty nice results. The 16-bit systems did exactly the same as the 15 bits, but they took into account that memory is typically aligned in an exponent of 2, in this case the 4th exponent, so in 16 bits. So 15-bit memory, right, doesn't really exist, so it's better to use 16 bits and just throw away 1 bit. Later, we started using 24 bits. So that is 8 bits for red, for green, and for blue, generating 16 million possible colors, which is good enough if the displays can actually display them to have all possible colors that the human visual system can perceive. And what was initially often done was, people said, well, our memory is aligned to either 16 or 32 bits, so we will use 32 bits of memory where we use 24 and we throw away 8. Later, in our modern systems, these extra 8 bits are being used to represent transparency, so that we can overlay images that are partly visible because they are semi-transparent. A very different representation of color that is still being used when we have very small devices with limited displays and with very limited memory is the 8-bit representation. Now with 8 bits, we could, for instance, say, well, let's use, say, 2 bits for red, 2 bits for blue, 3 bits for green, something like that, or 3 for green, 3 for blue, 2 for red. The results look awful. So what was done instead is that, well, with 8 bits, we can represent 256 values. We create a table in which each value is associated with a 24-bit color value. So we can represent all possible colors the human eye can observe, but we can only show 256 different colors at any one time. 256 is not a lot, but if you, for instance, consider, right, that with 24 bits we can represent 16 million colors, we currently do not have any computer screen with 16 million pixels. So we cannot show 16 million colors at the same time. Now, 8 bits, so 256 different colors shown at the same time may be a bit low as a number. The 16 million is currently still a bit overkill. So techniques in between are still valuable. Now, for your final project, you don't have to worry about the colors. We typically use 24 or 32-bit representation. The devices you will be working with have enough memory to handle it and have actually also good displays. Not good enough to show 16 million different colors, but good enough to give you the ability to create very nice icons, for instance, and show nice images on the screen without worrying, right, that the device may be the limiting factor. Thank you for participating.